AR and MR devices, how to model light guides in VirtualLab Fusion. The first point that I want to touch on is to say that this is not the first time that we discuss the topic of light guide devices for augmented and mixed reality applications in a webinar of ours. A few months ago, Professor 𝗃𝗲𝗀𝗲 gave an incredibly insightful presentation about the theoretical framework surrounding this topic. Now, today I'm not going to repeat what was said in that webinar, it's not needed. So, if you missed it, I would strongly recommend that you use the link we provide in the follow-up material that you're going to receive after the webinar today to access the video recording of that presentation, of that previous webinar, and the accompanying slides. Today, I'm going to use the discussion presented in that webinar as a springboard from which to start the discussion, as my starting point, to look at things from a different perspective. The main objective today is to provide our viewers, our participants of this webinar, with a bit of an impression of the look and feel of VirtualLab Fusion when it's used as a tool in the field of light guide devices for augmented and mixed reality. It's not a training course. We have very limited time, evidently, so the point is not for you to learn how to do everything exactly, how to follow exactly the workflows that are relevant in this field of application. The only objective is to illustrate what things look like, how things work, what the different features are in VirtualLab Fusion when talking about this topic. So with that, let's begin. Before entering the more hands-on side of things, I want to say a few words about the license model, only as it relates to this very specific field of application. So I'm going to talk about the additions, the toolboxes of VirtualLab Fusion, so that you get a bit of an idea of what the product structure is, if you're interested, in case you're interested in using VirtualLab Fusion, the tools that VirtualLab Fusion offers in the field of light guide modeling and design. So in general, our license model always starts with a VirtualLab Fusion platform. It comes in two editions, basic and advanced, and the only difference between them is that the advanced edition provides tools for the rigorous analysis of gratings, in particular the Fourier model method, FMM, also known as rigorous coupled wave analysis, RCWA. In the specific case of light guide devices, we would add additional toolboxes on top of this fundamental VirtualLab Fusion platform. In the case of the light guide toolbox, the basic edition is left out. It doesn't really make sense because of the fundamental role that gratings play. So in the case of light guide devices, we start from the advanced edition, and then on top of that we would add the light guide toolbox, which again comes in two versions: silver, which covers all the aspects of light guide modeling, of light guide device modeling, and then the gold edition, which on top of that adds some specific tools to aid the optical designer in their job of designing a light guide device for augmented and mixed reality applications. Today, we are mostly going to concentrate on the modeling part, so that's what we are going to mostly be talking about. However, I will pull some tricks from the gold bag and to make things a little bit faster. You'll see what I mean in a minute. And I will try to make sure that I point out in those instances in which I'm using tools that are specific to the gold version of the light guide toolbox. Next on the agenda, we have a very brief discussion of the basic functionality of this type of device. Again, that is discussed in much more depth in that previous webinar by Professor 𝗃𝗲𝗀𝗲, and I will urge you once again, if you missed that and you're interested, to revisit that material to catch up on that. The only thing I want to achieve with this today is to make sure that we're all on the same page, to give some basic definitions so that when we talk about things in the software later, we all know what we're talking about. So some key pointers about this general understanding, this general function of this type of device. So the basic scenario in AR and MR requires a device to fulfill a twofold objective. On the one hand, the user of the device needs to be able to experience the real world around them without obstruction, and this side of things is normally fulfilled by using a transparent light guide, a transparent device. That leaves the second side of things, the second objective that we want to achieve with this device, which is the superposition of an artificial image, a man-made image, on top of that experience of the real world. Of course, the device, the part of the device that generates the image, cannot be directly in front of the eye, because that would impede the fulfillment of the first objective. We still need to be able to see through. So we take advantage of the well-known total internal reflection phenomenon in order to transport the information of that artificial image from where it is generated to the eye of the observer. An added layer of difficulty is the fact that the detector is not static. We're talking about a human eye in its socket, which means it can move across a range of positions, and we need to ensure that wherever the pupil is in that range of allowed positions, the user of the device is going to be able to have a seamless experience with the augmented and mixed reality glasses or device. So that range of positions that we need to cover with our artificial image is what we call the eye box, and ensuring that wherever the eye is, wherever the pupil is in the eye box, that things function smoothly, that we have enough information reaching that aperture, that pupil, that is a fundamental part of this type of device. So as I already mentioned, we're going to be using the phenomenon of total internal reflection in order to transport that information from where it's generated to the eye. And now let's talk a little bit about the shape that that information takes. So we're going to generate an image on the basis of pixels. We're going to generate a pixelated image, and we're going to function under the assumption that each of those pixels generates a spherical wave. It acts as a point source, which is then collimated. And so from the imager, what we obtain is a plane wave with a given size, with a given lateral extension, and that's what we need to transport. Again, that's for 1 pixel of the image. In order to couple that plane wave into the device so that it can be transported under conditions of total internal reflection, we use an in-coupling grating. We all know that it's a very elegant way of achieving that purpose. And then for exit pupil expansion, that is related to what we just mentioned, that we need to be able to cover the whole range of positions of the eye with the functionality of our device, and then also for outcoupling the information so that it reaches the eye, we use also gratings. And we know that the eye functions very well when it receives the information in the form of plane waves, because it will then focus that onto the retina and form the image again. Then for another pixel, we're going to have, after collimation, a different plane wave with a different direction, which also needs to be transported under total internal reflection to the outcoupling grating and to be coupled out. So the range of directions, what we call the field of view range, defines the size of the image that we are going to superimpose, the size of that artificial image. So let's not waste any more time, and let's directly go to VirtualLab Fusion, to the more hands-on part of the session today. Again, the point of this is not for you to learn to do these things yourself. This is not a training. It's more to give you an impression, to give you a feeling for how things work, what things look like in VirtualLab Fusion when one uses this fast physical optics modeling and design software in the field of light guide devices for AR and MR applications. I also want to emphasize once again that we're going to keep the focus on modeling today. Design, or the bulk of design, we will leave to a later installment of this webinar series. However, I already said that I would pull some tricks from that gold edition of the Light Guide Toolbox in order to move things along a bit faster. And I'm going to actually start with one of those tools from the Light Guide Toolbox Gold Edition, and that's the layout design. This is we are just going to enter some parameters about the system that we want to obtain into this layout design tool, which is the one that we have open here. And then we click a button, and that generates already a light guide system with a specific layout. This tool works particularly for 1D EPE type layouts of light guides, in other words, for HoloLens 1 type layouts. So we have 3 tabs in this tool to enter parameters pertaining to the incident light, to the light guide device itself, and to the outgoing light. We configure things according to our requirements, to the device that we want to obtain, and then simply click on Create Result, and we obtain a series of documents that we will go through in a minute. So here on top we have the system that has been designed. We will talk about that next, but first I want to give an honorable mention to this K-layout visualization tool. This type of document can be generated also standalone and played with on a standalone basis, not just as the result of this layout design tool, and we can find it here, K-layout visualization. Again, this also pertains to that HoloLens 1 type layout, and it's available in the gold edition of the Light Guide Toolbox. More about the topic of this K-layout visualization of the system in that previous webinar with more of a theoretical discussion by Professor 𝗣𝗲𝗀𝗀𝗀. Today, let's just say that this provides us an alternative perspective with which to view the function of our device. So, we already said that the range of field of view is one of the fundamental parameters. It's going to define the size of the artificial image that we can generate on the retina of the observer. So this range of angles, this range of directions, if we plot them on a kx, ky wave, this would be wave vectors, on a kx, ky plot, then we define something that looks like a distorted rectangle. The distortion comes from the non-linear relationship between the k components and the angles. There is a trigonometric relationship, of course. So this defines that range of field of view that we want to work with in this device. Then this first circumference, the smaller one, defines the propagation condition in the embedding medium. In this case, we have air. And the outer circumference defines the propagation limit for the material that is used in the waveguide, in the light guide, as defined here. So the total internal reflection condition corresponds to this green, to the shaded area in green sandwiched between those two circumferences. So we start from our field of view range in air, and we use the in-coupling grating. This here would be the grating vector of the in-coupling grating to couple light into the light guide. Then we use our eye pupil expander grating, which will induce this grating vector here, and then we couple light out. Now, because the initial field of view range and the outcoupled field of view range coincide, we have exactly the same range of directions. We cannot actually distinguish them here, but if we change the parameters slightly, we can we can see that we have the two here. I have simply changed the orientation of that 𝗃𝗃𝗀𝗀𝗃 grating slightly. But of course we want to retrieve the same field of view when we couple out as the one we coupled in. So the correct configuration is this one where both coincide. That's it for this tool. It gives us, the main takeaway here is that it provides a very intuitive way of analyzing the behavior of this type of device. But let's now turn to the system. I'm also going to minimize this layout design tool. So next, let's talk about the system. Now, the configuration of the system is completely flexible. We can set up from scratch any light guide device with any sort of configuration we want. In this case, I took advantage of that layout design tool in order to get a working example, something that would allow me to showcase the features that I want to show quickly. But we could have done this exact same definition from scratch by ourselves. We have complete freedom, complete flexibility there. The system is composed of two possible sources, two available pre-configured sources. One is a plane wave. This already has that finite lateral extension. We ignore the imager for at this stage. It could be included. We could include a point source and the collimating system from which we get those collimated beams. However, we're going to limit our analysis to the light guide device purely. So we already assume that the input of our system are the collimated beams, those plane waves, those that set of FOV modes. So this plane wave would be one of those FOV modes. By default, it's going to be the on-axis one, 0, 0 direction. The scanning source already contains a pre-configured set of FOV modes so that we can model them all simultaneously. Then we have our light guide device and detector placed at the position of the outcoupling grating in reflection. This is a system that works in reflection. I'm going to start by running the simulation with the ray tracing system analyzer, which provides a 3D ray tracing view of the system. Here we have it. I'm going to switch off the rays for the time being so that we can take a look at the bare bones system. Here we have it. We start here with our plane wave source, which is going to be generating that central FOV mode, in-coupling region, EPE region, out-coupling region, and this red square is the detector. I'm going to switch on those rays again so that we can see the progression that the light follows through the system. We can see this, that central mode propagating to the region and then being coupled into the light guide, being totally internally reflected, then interacting with that EPE region and being diffracted sideways as well as reflected on by that zero reflection order. And then we reach the outcoupling region that also takes care of the eye pupil expansion in the other dimension, and finally light being outcoupled and propagating onto the detector. Now this is a very clean view of things because we're using a filter that only shows us the rays when they eventually go on to reach a detector. But we can switch off that filter right here and run the simulation again to take a look at the stray light in the system. And here we have it. Same situation, it's exactly the same simulation, only we are seeing that stray light in the system. And we can very clearly see one of the sources of interesting effects or complex effects in this type of system, which is that partial interaction of some of the footprints with the interfaces that define the light guide and the grating region. So this footprint here, for instance, is partially totally internally reflected and partially interacts with the grating region. And the same is true for many other footprints here. This will have effects, this will produce aperture effects, because of that boundary that will be reflected in the beam profile, as well as effects on the polarization state of the beams. And these effects build on top of one another because, of course, there are many different interactions with the different grating regions on the surface, etc., etc. So that is one of the most interesting aspects, or one of the most complex aspects here in this type of system. Next, I'm going to swap the source so that we can observe that FOV range simultaneously, all those FOV modes simultaneously. And we're going to be using 9 different FOV modes. Let's take a look at it here. So we have 3x3 plane wave directions that we're going to be generating in this range of field of view, 32 degrees by 18 degrees. I'm going to run the simulation again with that ray tracing system analyzer. We're still going to be seeing the stray light in the system. And here it is. Of course, it's a lot more chaotic now, even more complex. Everything has been colored according to the wavelengths. We only have one wavelength at the moment in the system, but we can also separate by color. We can color the rays in a different way here, say by lookup table, and each of the FOV modes will be colored in a different way so that we can better distinguish what's going on here. So let's zoom into that initial part. We can see that range of directions now that enter the system. We can see those different FOV modes interacting here with that incoupling region, and then how each of them travels differently through the system. Of course, it's still there's a lot of information here provided at the same time. We can visualize each of the FOV modes here independently. So we have the 9 FOV modes, and we can go through them, see the behavior of the system for each of them. We see how this region, the shape of this region, has been defined according to that FOV range, so that the system works for the FOV range that has been defined in that layout design tool that we called on at the beginning. So we can go through and see all those FOV modes and how the system works for them. Next, I want to talk about the grating regions, how they're configured and the possibilities that they offer, etc. So I'm going to double click on the light guide component to trigger the configuration dialog. And the first thing we see is this preview of what the device looks like with different shades to indicate those grating regions on the surfaces. In this first part of the configuration, we can define the surfaces and the media that define the device. We're not restricted to plane surfaces either. We can select from a range of shapes, also with sampled and programmable options to offer full flexibility. And also, again, the media that are used to construct this component are listed here and can be configured here. In this other tab, we have the surface layouts, and we can configure different layouts on different surfaces independently. According to the current system that we have in our hands, all 3 regions are in this first plane surface, and we can investigate them. We have our incoupling region, our expansion region, our expansion grating, and our outcoupling region. We could add more, and let's add another one. Let's add a new one to take a brief look at the possibilities that we have for the definition of the shape. So this is the dialog to set up a new region, and here we can investigate the options that are offered to us. We have a few default ones: rectangular, elliptic, simple polygon, which is the one that is used for the EPE region, for instance, where the positions of the vertices are provided, and that defines the region, and you can enter as many vertices as it takes to define that polygon. But we also have the full flexibility once again offered by the possibility to import a sampled region, and it's possible to build more complex regions, more complex shapes by a combination of basic ones. Another feature worth mentioning here is this gridded segmentation that allows us to subdivide the regions that we have defined, these areas, into subdivisions, sub-regions, according to, for instance, this configuration. We can also enter a value here of the orientation of that segmentation angle. This is quite handy in order to vary the grating parameters over one of these areas, as is customary, in order to optimize the efficiencies of the working orders to ensure that the function, the intended function of the device, is realized. Then each of these regions, once we finish this segmentation, each of these regions is going to be independent, whether the vertices remain linked, so that if we change the position of one of these vertices, the adjoining regions will also change accordingly. There are options to control that, so it can be activated or deactivated. And then the grating parameters, we're going to talk about ideal and real gratings in a minute. The grating parameters are completely independent for each of these regions. So once again, this goes a long way towards providing that full flexibility of configuration of the system. Next, let's go from the regions themselves to the gratings that are contained in them. So let's take the incoupling region as an example, but the same, of course, would apply to all the other regions independently. This is a configuration dialog of that region. First we have the shape, this we have already seen previously. Then the next step is the region channels. We can completely independently define the channels for each of the regions and for the surfaces in general. So the 4 channels here correspond to transmission for light propagating in the positive Z direction, reflection for light propagating in the positive Z direction, transmission for light propagating in the negative Z direction, and reflection for light propagating in the negative Z direction. So we have those channels, reflection and transmission in the other in one direction, reflection and transmission in the other direction. That covers all possibilities for a surface or for a region. Then, of course, in these regions that we have defined, we have gratings, which additionally include or bring with them the added variable of grating orders, and that's what we have next. In this next tab, we can define everything pertaining to the grating, and we can choose whether to propagate only a set of specified orders. In this case, we're talking about the incoupling grating, so the orders of interest are the +1 order in transmission. That's going to fulfill the condition, or that's going to realize the condition of TIR, but also the 0th order in reflection, because it can be possible that after the first reflection of that incoupled beam with the backside of the light guide, when the beam travels backwards towards that first interface, that it once again interacts with the grating region, with the incoupling grating region. And so to take that into account, we have defined this as well. And these are, because we're working under this specified orders configuration, these are the 2 orders that were simulated when we performed the ray tracing simulation. And currently, let's go to the efficiencies tab. Currently we're working with idealized gratings where we manually fix the efficiency of these orders. This can be useful for a first approach to the device, or in case we're trying to simulate something but we don't know exactly the parameters of the grating that is used there, then we always have the choice, the option of working with these idealized gratings. Let's try running the simulation next with all orders for this, or propagating orders for this in-coupling grating, and I'm going to remove the orders, I'm going to remove the defined orders here so that the efficiency, the energy, is distributed homogeneously over all possible orders. So with this configuration, I'm going to run the simulation again with the ray tracing system analyzer. Again, just the central FOV mode. And we can observe here, for instance, this additional, this minus first order. We can also see the 0th order in transmission. So it is possible to use those different definitions depending on what effects we seek to observe in the simulation. We have full control of what is included and what is shown. Let's next talk about the possibility of using real gratings in our grating regions, and I'm going to be working with the in-coupling grating region as an example, but again it works in the same way for all of them, for every possibility. So I'll go to this grating tab here, and I have retrieved the previous configuration where we're just working with the specified orders here. And I'm going to the efficiencies tab and selecting now from real gratings. And now, of course, we need to define the particular structure that is going to, that grating is going to have. So the shape, the modulation depth, everything needs to be determined now. While for ideal gratings, it is enough to fix the efficiencies and to provide a value of the period, because the period determines the deflection of the different orders. Now we need to make sure that we define a specific structure with the shape, with a particular shape that structure is going to have. I want to mention that VirtualLab Fusion provides additional tools for the analysis of gratings in an isolated way, what we call grating optical setups, and there we can work with the grating as standalone component and analyze its behavior with respect to different variables, optimize it as well. Then we can save that structure and import it into our light guide, which is what I'm doing now. I'm going to import a predefined grating, in this case this coupling grating binary, which I pre-configured and saved to the VirtualLab catalog, and now I'm simply going to import it into my in-coupling region. So now I have a real grating in this region, and this the behavior of this grating is going to be simulated with the Fourier model method, a rigorous approach, a rigorous solver for periodic structures. We can configure the numerical parameters of that algorithm here. And then we see this option here at the bottom, lookup table. The lookup table concept is an extremely powerful one. It saves the information, it runs it, so we would run the simulation once for this configuration of the system with this specific grating. And the information of how that grating transforms the field for different wavelengths, for different incoming directions, and for different predefined orders. That information would be stored after the simulation is run once, so that then when we repeatedly perform simulations with this system, that FMM, that rigorous analysis of the grating, does not have to be repeated, and we save on simulation time. This is an extremely powerful concept. So let's right now, we have just configured this structure here, so there is no information for this lookup table. There is nothing here. The next time the simulation is run, this characterization of the grating is going to have to be performed during the simulation, but then that information is going to be stored and reused for subsequent iterations of the simulation. So I've run the simulation with the field tracing engine to produce this result, and I increased the size, or the lateral size, of the initial beam slightly. I had decreased it in order for things to be more clearly visible in the 3D ray tracing of the system, so that we could clearly make out different steps. But I have brought it back to the initial configuration, so that's why we now have some overlap. We can see those partial interactions of the beams with the different boundaries when they are partially totally internally reflected, partially interacting with the different grating regions in the system. All that can be seen here. And now that we have run this simulation, I did it off camera so that we could save some time. The simulation took a bit over a minute. Now, if I go back to that configuration dialog of the grating region, we're going to see that the information has been stored for that lookup table. Okay, we have this information now. This feature, this very powerful feature of storing the lookup tables for the gratings, is particularly powerful when we have variable grating parameters in our system, because of course then we save a proportional amount of simulation time if we have that information stored in advance. Another tool that is worth mentioning in relation to this whole thing is the grating channel analyzer. It allows the user to define their own custom Fourier model method if that is of interest to them, instead of the default one that we provide in VirtualLab Fusion to perform this analysis. And then if running the simulation with this grating channel analyzer looks for situations in the system for which no lookup table, no valid lookup table exists, and if any of those situations, if any of those lookup tables are missing, it calculates them. So it's possible to run the simulation with a grating channel analyzer overnight, maybe before you while you're not using your computer. So you make the most of your simulation time. You can leave it running, the lookup tables will be stored, and then later on you can work more comfortably. In this case, it has told me that no new channels were determined, no additional calculations have had to be made. By the way, this system that I currently have on currently have open has all gratings defined as real gratings. So the in-coupling, EPE and out-coupling gratings are all real gratings in this system. And now let's talk about additional possibilities for the variation of the parameters. And in particular, I want to talk about a feature called parameter modulation feature. I'm going to the, let's say, the expansion grating, the EPE grating, to this grating tab, and to this efficiencies tab again. And we see this option here, use modulated grating parameters within region. Now this option is available in the silver edition of the Light Guide Toolbox. However, the necessary tools to fill this this feature, to provide the necessary information, those lookup tables for the modulated parameters, that feature needed to feed this the lookup tables for the modulated grating parameters is provided with the gold edition. So one can define the modulation, but the tool needed to feed it is part of the gold edition of the LightGuide toolbox. And I'm going to close this here because I have a predefined system. This is the same system, but it already includes that modulation, that parameter modulation for the EPE grating. And let's take a look at what that modulation, what those modulated parameters look like. So here in the efficiencies tab, this option is active, and we have used already the additional design tool to feed it, to feed the lookup tables of these modulated parameters. So the parameter that we're modifying here, and we can select up to 2 parameters per region, say the fill factor and the modulation height of the structure. In this case, we have just selected one, the fill factor. From 10% to 90% is the variation, and we can look at that modulated parameter across, at the values of that modulated parameter across the region. And this can be defined via sample data, or we can also define a programmable function to define this variation of the modulation of the grating parameters. This modulation, of course, this possibility to modulate the parameters of the grating can then be used in an additional optimization of the system. We have so far said quite a bit about the configuration of the system and adjusting it to have exactly what we want to have. Let's devote the last few minutes to highlighting the physical effects, the physical phenomena that we can analyze after having configured our system. And I'm going to start with polarization. I have the same system here that we have been working with throughout the session today. The plane wave is going to generate EX polarized light. The angle of polarization here is 0. So at the input, we only have that EX component. However, the light is going to travel very haphazardly through the LightGuide device. As we know, it's going to hit the interfaces, it's going to hit the different grating regions, and so on and so forth. And that is going to cause polarization effects. That's going to generate a crosstalk from that initial component EX to EY. So I've configured the camera detector by selecting only the EX component to integrate, and then conversely only the EY component to integrate. And I've run the simulation with those 2 different configurations, and this is what we obtain. Remember, the input is just EX. The scaling here has been adjusted so that both documents show exactly the same thing, or the same scale, the same values of the scale. And we observe that main component in our system, EX, and the effect of the crosstalk that has generated the presence of a certain EY component as well. Next up is the simulation of partial temporal coherence. So far we have been working with purely monochromatic sources, and now let's take a look at the different strategies available to tackle that side of things, to simulate sources with partial temporal coherence. Let's start with a rigorous way of doing things, which requires generating a wavelength spectrum for our source. We have some predefined options to select from here, as well as the full flexibility provided by a data-based spectrum that we can import, or a programmable spectrum that we can fully customize. So I'm just going to generate one, and this will produce the needed data, this wavelength spectrum for our source, which we then need to import into the source under the Spectral Parameters tab. But there is another possibility, and this is an approximation, but it requires a lot less computational effort, simulation effort, and simulation time. It is via the detector. So I've double-clicked on the detector to trigger the configuration dialog, and we see here that under coherence parameters, we have the option to select partially coherent summation. And then the only information that we need to enter is the coherence time of the source. In the next couple of slides, we can see a comparison between the two methods. So we have a similar system. It's not exactly the same, but it's very similar to that one we have been working with. And we're going to check out the results for both models, where we input the actual wavelength spectrum of the source, and when we take that approximate approach in the detector of entering the coherence time in the detector. And we're going to see the results of the simulation for 3 values of the bandwidth: fully monochromatic, that is fully coherent, and then for a bandwidth of 1 nanometer and of 10 nanometers. And that's what we see here: fully coherent, 1 nanometer bandwidth, 10 nanometer bandwidths. And this is the rigorous model, the frequency model. Here we have we take into account the full spectrum, we simulate all the wavelength modes propagating through the system, and then add them together to produce the full result. And on this next slide, we have the temporal model, that approximate approach via the detector for the same 3 situations. The main difference is, as we can see if we go back and forth, is the fact that the temporal model does not include the angular dispersion and the resulting shifts of the different spectral modes. So that is the difference, the main difference between both approaches. Finally, let's mention the inclusion of diffraction. So far we have neglected diffraction in the system, and this whole topic is related to the Fourier transform configuration in the system. It's a very complex topic. I'm not going to go into any depth here. We have additional documentation on our website. But for now, suffice it to say that I'm clicking on the simulation settings of the system, and I'm going to field tracing. Suffice it to say that we have a catalogue of Fourier transform algorithms available, and in general, when all options are activated or allowed by the user in the configuration of the system, the most appropriate choice is selected. And this catalogue of Fourier transforms includes 2 algorithms, the fast Fourier transform and the semi-analytical Fourier transform, which are rigorous operations. And then there is the third one, the pointwise Fourier transform, that is an approximation that neglects diffraction. So when diffraction effects are not important, it is a very good approximation. But when we enforce the choice of this pointwise Fourier transform, what we do is neglect diffraction in the system. And so far, this is the configuration that we have used. We have only allowed this pointwise Fourier transform throughout the system until the detector. Now we can activate everything here for throughout the system, okay? So now everything, all the options are allowed throughout the system, and then the automatic decision-making algorithm, the automatic decision-making process is going to take over, and it's going to decide every time a Fourier transform is needed in the system which one is the most appropriate one. So now diffraction is going to be included in the simulation. The simulation is going to take longer because those rigorous Fourier transforms are heavier to calculate, but it is a way of visualizing those diffraction effects throughout the system, and this can be caused by the finite size of the initial beam, and every time the beam propagating through the system hits one of those boundaries separating the different regions. Once again, we can see on the slide the simulation results for a system very similar to the one we have been working with, and we can see the effect of considering diffraction in the simulation. So on the left-hand side, we have the simulation without diffraction. On the right-hand side here, on the right of the slide, we have the simulation with diffraction, and we see those typical ripples that are caused by those boundary effects and the different apertures that have an effect in the system. That's it from my side. Thank you for listening, and let's open the floor for the Q&A.